There you go, close. That should do it. Okay, so we should be back now, I'm hoping. Let me know if you can hear me. Maybe we just need to give it a couple seconds. Good to go? All right. Hey guys, sorry about that. Go ahead and drop me back in there. Wow. I guess we're all getting used to this kind of stuff. Thank you guys for hanging in there. I really appreciate it. I'll go ahead and jump back a couple slides and catch you up to speed here without sparing any details for you. But again, I'm Joe Schoonover from Fluid Numerics. We're going to be talking about some WRF benchmarks today. And specifically, we'll be covering a lot of the stuff we did to encapsulate this solution so that you can run it on your own as well. And then of course, we'll share with you the benchmarks that we obtained in the last couple months working with Google to give you an idea of where things are currently at. So we'll go back over this slide here. So the key ingredient here for getting all this off the ground to make it reproducible for you to use is what we call an image bakery. This consists of 3 basic ingredients. Primarily, we have a Git repository, which is this Fluid Numerics HPC apps GCP repo. We connect that to a service to do continuous integration and continuous deployment. And here we're using Google Cloud Build so that anytime I make a push to a particular tag or a particular branch on this repository, the WRF image will get built. So we are actively maintaining this repository and trying to put in all the improvements as we find them and as things go. Now on the other side of this, underneath Cloud Build, we use a tool called Packer, which is from HashiCorp, and this allows us to kind of encapsulate very nice and neat the instructions necessary to spin up a VM image on GCP, execute all the instructions we want to install WRF and its dependencies, and then snapshot that image and tear that whole system down. So at the end of this, basically we can just create new versions of this image just by pushing commits to the GitHub repository and letting the images come out on the other side. So I do want to talk about some of the ingredients, and this is kind of where I left off before we got the audio issue figured out. I want to talk a little bit about some of the ingredients here that go into actual image baking. So at the top level here is an install script. In this case, it's just a shell script. So if you're in that repository, you go underneath the WRF directory, you'll see all these things there. But that shell script contains all the instructions necessary to install WRF and its dependencies. In our case, we're using a GCC 9 OpenMP, OpenMPI 4.0.2 stack to install WRF. And of course, this includes everything like HDF5, NetCDF, Jasper, libjpeg, all those things that WRF depends on to get going. Underneath the etc directory, we have customizations for the operating system that include a lot of stuff that Google has recommended as HPC best practices. And these are things that really just allow you to run jobs with a large number of MPI ranks. They give you a bit better performance on the networking infrastructure that's there. And of course, it opens up the possibility to run really big applications for long periods of time through like the security limits, conf modifications. And you know, basically that's all that's going in this directory. So that during the image baking process, that etc directory gets copied up onto the virtual machine image that's used for baking. And those things get saved into the VM image. Then we've got 2 real configuration files. One of them is the configuration file for Packer, and this just controls the size of the instance we use for that image baking process to create that virtual machine image, and then all the steps necessary to get that installation done. So it tells the system, hey, we need to run this install that sh script. We've got to copy that etc directory up and get it into the VM, and then of course Packer handles for us doing all the node provisioning, snapshotting, and tearing down of that instance. Then down at the bottom is this Cloud Build configuration file, and this is what enables us to connect with Google Cloud Build so that we can do the automated testing and baking of those images upon commits. I think in this case we only build on tags to that repository that have the word WRF in them. But this really all it does is just provides those instructions to execute Packer every time we push a WRF tag to the HPC apps GCP repository. I do want to briefly touch on that install that sh script because there's a lot of ways you can install WRF and all of its dependencies. A couple years ago, I would normally just write a really long shell script to go after reading documentation, install all the dependencies, install the compilers I want, and then install WRF itself, and this is, I mean, you can easily end up with a 1,000-line shell script this way, but we opted to go ahead and just use SPAC, which makes life really easy, because you can encapsulate basically the installation of WRF and its dependencies into this, what I have is 2 lines here on the slide just to make it fit, but we can basically say, hey, I want to install WRF. If you're interested, yes, we are working with WRF version 4 in these benchmarks. We give it the compiler that we're going to use again, which is GCC 9.2, and then we've got the OpenMP we want to use. Now, in our script, we've added some other stuff in the background there that allows us to leverage the Slurm GCP solution. And we'll talk a little bit about what that is in a minute, but ideally, basically, we're setting up this build so that it can integrate with the Slurm job scheduler on Google Cloud. So here's the basic infrastructure we started it. So now that we've got a virtual machine image, we need a way to deploy this on Google Cloud. And again, all this stuff we've encapsulated in a Terraform subdirectory underneath WRF on that HPC apps repository. And so that you can recreate this cluster. But what we wanted to do was have a system that had a very similar look and feel to what you would use on premise. So you have a login node where you can hop into the cluster and interact with the Slurm job scheduler. We have what's called a controller, which is really hosting out of the box your home directories over NFS, a directory called apps where WRF actually ends up being installed. And it basically, this houses the Slurm controller daemon and the Slurm database daemon. It kind of is the brains of the whole operations here. So whenever you submit a job, that controller takes care of making the appropriate calls to the Google APIs to spin up these elastic compute nodes, so that compute nodes are only coming up when jobs are being submitted. And of course, once those jobs are completed, they get automatically taken down by that controller as well. Now the deal is when you're running on GCP, there's a lot of different machine types that are available. And so there's an obvious question of, well, which machine type is going to be best for my application? And really to answer this question, what you got to do is actually just run through the comparisons and take a look at what metrics matter to you. Now for us, in this study, we focused on 2 things. One, the speed. So how fast can I get a simulation out? And we measure that as the ratio of the simulation time divided by the wall time. And so what that gives you is, if you had a speed of 1, for example, the amount of if you had a speed of 1, I'd basically be getting out 1 hour of forecast time for every hour of wall time. And of course, anything greater than 1, we're now putting ourselves in a scenario where we can be doing forecasting. All right, so what we want to look at here, in addition to speed, because you're on cloud, you get billed per second for every compute cycle that you use. We actually start to calculate the cost, which is really a function of how many nodes you have multiplied by the wall time and then multiplied by whatever that cost is in the GCP price book. So let's take a look at that on the next slide, and I'll explain to you what each of these machine types are here. So on GCP, you have what are called C2s, you have N2s, N1s, and N2Ds. So starting on the left, the C2s are Intel Cascade Lake CPUs, and they're set up in such a way that the guest operating system that the virtual machine actually runs in, it maps the core layout. The logic of the core layout is mapped 1-to-1 with the host operating system, so you get a direct mapping to the underlying hardware on Google Cloud with the C2s. They're called compute optimized Intel Cascade Lakes. And we got the N2s, these are also the Intel Cascade Lakes, but they just don't have that 1-to-1 mapping. Then the N1s, when you run with N1s, you get either an Intel Broadwell or an Intel Haswell, but still in that E3 generation of the Intels. And then the N2Ds are the AMD EPYC Romes. Now that number on the side there, that 96, the 80, the 60, that refers to the number of virtual CPUs or the number of hyperthreads that you get access to on those instances. And in all these cases here, I picked the largest possible machines we can have, so you have the most number of vCPUs available on each of these machine types. And we essentially ran through a bunch of different configurations with the CONUS 2.5 kilometer benchmark running for 6-hour forecast using 480 ranks. We played a lot with the Affinity and all these things, and what I'm showing you here is the runs for each of the machine types that give us the best speed and the lowest cost for each category. Now, of course, if you compare these, the C2 standards obviously have the highest speed for this particular configuration, coming in about 7.6 times faster than reality. And they also came in with the lowest cost, and that's presumably because the per node cost, the per core cost in this case is roughly, they're very similar, they're close enough. because the simulation time is so much faster on the C2s, we're able to get that lower cost in there. So in everything I'm going to be presenting in the following slides, we're really just focusing on the C2 standard 60 instances. So these are the compute optimized Intel Cascade Lakes. Now I want to talk to you a little bit about some of the affinity testing here, because task affinity really makes a big difference in terms of performance. And like what I mean by task affinity is, well, you got this pool of resources. You got all these cores laid out. They're distributed into sockets on a motherboard, and those motherboards are in servers, and those servers are distributed in some way in a data center. And the task affinity refers to how you lay out the MPI ranks onto those virtual CPUs that you have available. Okay, and we have two ways of doing this. If you're working with the Slurm job scheduler, for example, you have where you can request what the resource allocation is per task in the batch header if you're writing batch files. And we're focusing primarily on modifying that using the n tasks per node and the CPUs per task parameter. Now, in this particular configuration, if I'm running on a C2 standard 60, I have 60 virtual CPUs. That really means is I have 30 actual physical cores, and each core has 2 hyperthreads on it. So if I, for example, wanted to put a single MPI rank onto each physical core, what I could do is say I want 30 tasks per node, so I'm only going to put 30 MPI ranks per node. So tasks and MPI ranks are equivalent here. And then I can say that each task is going to get 2 CPUs, right? So if I've got 2 CPUs per task, basically what I'm saying is each rank is going to be able to leverage both of those hyperthreads that are there. Now, if you take that and you compound that with what are called affinity flags with MPI run, and you can do similar things with Slurm's srun to do this kind of binding. We use this bind to option to basically restrict the MPI ranks from migrating out of a physical core, because if you don't bind it, what can happen is the MPI ranks are free to move around to different cores on the same node that they're subscribed to. And that kind of migration or eviction process can add some overhead. So binding when you can actually help improve performance. And of course, the choice you make on what you actually bind to, how much freedom you give those MPI ranks to move around, can also change performance. And a lot of this depends on, in the end, the ratio of the amount of memory operations you're doing for every flop, or what's called the arithmetic intensity. So although we didn't look detailed into arithmetic intensity, what we're doing here today is just trying to figure out what would be interesting cases to look into to do roofline modeling and some more detailed profiling. And the way we're doing that is just by modifying this parameter here, the bind to. We switch between either cores or hardware threads, so we can test where things are at, whether we enable or disable hyperthreading. When I say disable hyperthreading, essentially I'm giving, in that case, each MPI rank a full core. When I enable hyperthreading, each MPI rank gets its own virtual CPU, or it runs on that hyperthread. And there's just a lot of discussion around whether or not this is a good idea for some applications, and I'll show you that it's not really a straightforward answer. In another case too, WRF has the option to build in a flavor, I guess you could call it, where you could have both MPI and OpenMP. So you have shared memory parallelism with OpenMP, and you have distributed parallelism with MPI. And what this can allow you to do, if I were to, for example, take that same sort of layout, that 30 tasks per node, 2 CPUs per task, if I were to build WRF with MPI plus OpenMP, I can now say, for example, give each MPI rank 2 OpenMP threads. If I give each rank 2 OpenMP threads, then what you also want to do, bind that MPI rank to a physical core, okay? And once you bind that rank to a physical core, you can then start to really hone in on those OpenMP ranks and bind those individual OpenMP threads to the hardware threads underneath. So we'll be looking at some comparisons with that particular configuration as well. So that's what I'm showing here in this table. So I'll kind of walk you through this here, as we'll be looking at a couple of these in the next couple slides. We have the S-batch flag, so the things that control how many resources we're putting on a particular node, how many CPUs we're going to give to each MPI rank. Then we get the MPI flags, or the affinity flags that we're using, so whether we're binding to cores or hardware threads, whether or not we're using OpenMP or not. Then I've got over here for you some of the output metrics, you could think of it as, for the CONUS 12 kilometer benchmark here. In the next couple slides, we'll look at CONUS 2.5 as well. Now the blue row is the blue is indicating that we have, this is going to be our configuration that gives us the optimal compute time, and the green is the one that gives us the optimal cost. And you'll notice already that these two are not the same thing. And of course, there's a lot of reasons for this, but for CONUS 12, we got to look at this in a little bit of detail. So let's kind of go at the top. What we found is that the optimal compute time was achieved if we build with MPI plus OpenMP. We give each MPI rank 2 hyperthreads, so they get a physical core, and they get 2 OpenMP threads per MPI rank. And then again, each of those OpenMP threads are bound to a hardware thread. We run this, when you do the 2 vCPUs per task, we end up getting 16 nodes. And the compute time that I'm reporting here, so if you're familiar with WRF, you can usually think about breaking out the total wall time as the initialization time, the time spent in actually forward stepping the model and doing the forward integration, which does include a lot of MPI communications, and then you've got file I/O. So what I'm reporting here is just the compute time, and what I'm reporting in the node seconds is just the number of node seconds spent in compute time. As I'll show you in a little bit some stuff you need to do to improve file I/O performance. So anyways, when we use MPI plus OpenMP for CONUS 12, this gives us optimal performance. Now, the reason why I've capped ourselves at 480 ranks is if really you go beyond about 500 ranks with CONUS 12, you've exposed all of the parallelism in the problem. And you're physically not able to decompose that grid any smaller or into any smaller tiles. And you've kind of reached this limit of how much parallelism you can draw out of the system. And so if you want to get better performance, then yeah, adding more compute resources and then figuring out further how to use shared memory parallelism on top of that is absolutely important for squeezing out the every last bit of performance necessary for that size problem. You'll notice that, of course, running with 480 ranks on the CPU with 2 CPUs per task, so essentially disabling hyperthreading, we still have 16 nodes, but we're not using OpenMP. The performance is really not that much worse, but might as well use the OpenMP and get something a little bit better. And of course, if I'm still running with 480 ranks, if I just drop that back and I just say, you know what, I'm only going to use 8 virtual machines. I'm going to let the MPI ranks take over all the hardware threads. Yeah, the performance definitely is noticeably different. However, because you've been able to cut the node count in half, the cost is a lot less. The number of node seconds you're using has dropped. And so really what this ends up meaning to me, especially as an integrator or even as a researcher who might have to pay for compute resources, is I need to understand what the cost benefit is for having the solution that much faster and whether it's worth it to save that money. But we're laying this out for you guys so you can make that decision. So let's look at CONUS 2.5. We're going to do the same thing. On the top 2 rows, we're looking at 480 ranks. We're doing straight MPI builds with CONUS 2.5. We didn't look at anything with OpenMP here. And then on the bottom row, we're using 960 ranks, and I'll explain why in just a second. So if I go ahead and just, I guess we'll work our way from the bottom up here. We'll start with the fastest run, not necessarily the most cost-effective run, and work our way back. So the fastest run we could get is if I just said I want 16 nodes, all right, and if I just bind each MPI rank to virtual CPUs, so I'm using the hyperthreads on those nodes, I can get that compute time down to 490 seconds. So keep in mind here we're CONUS 2.5, so if you're trying to compare with the previous slide here, CONUS 12 had far less grid points. CONUS 2.5's got a bit more resolution to it, so in case you were wondering. So if I run with 960 ranks spread across 16 nodes using all those hyperthreads, I get the best possible runtime. But if I go back and say, well, if I have 16 nodes and I just wanted to disable hyperthreading, what's the compute time there? Again, we do significantly worse. And so in this case, if the reason why this happens is because with CONUS 2.5, there is definitely enough parallelism to expose. We're just going ahead and adding more MPI ranks and really breaking that problem down and distributing that across MPI ranks. There's enough of a performance gain there to where things like disabling hyperthreading don't really matter. And so again, a lot of these things I'm going to tell you today, it's really worth it for when you're thinking about migrating to the cloud, doing these kinds of suites of benchmarks for the problems you're specifically interested in. Because the results we're sharing today are specific to CONUS 2.5, they're specific to CONUS 12, and it certainly is interesting to think about, based on the size of the problem, where do we end up? Now in terms of the run that gets us the optimal cost, of course, going back to using fewer nodes, of course, is always going to give you an optimal cost. And I think that's just a universal truth that's just coming out of this to some degree. We run with 480 MPI ranks. We use the hyperthreads. Although we get significantly worse performance, in fact, the worst performance of these three that we looked at, but the node seconds came out to be quite optimal. And this is generally the case with tightly coupled applications where ideal scaling is not really a thing. So of course, as you add more ranks, you add more MPI overhead, more time spent in those MPI communications, and so the overall node seconds continues to climb up as you expose more parallelism and you bring that runtime down. So again, it weighs into this cost-benefit analysis that really needs to be done when considering, well, what is the value of really having the solution that much quicker? All right, so let's talk a little bit about how to improve file I/O. So, in most cases, out of the box, CONUS 2.5 and CONUS 12 are configured to run with serial file I/O over which really what that means is all the MPI ranks gather or send their data to the root rank. The root rank blocks everyone from proceeding, and while it tries to write out to disk to NetCDF, and then everyone's free to move on from there. So what you can do in WRF is you can change the I/O form for both the restarts and the history files, for example. Set them to the 102 setting, which is asynchronous parallel file I/O. So each rank writes its own NetCDF file. Okay. Now that gets you part of the way there, but what you can also do is run parallel file systems in the cloud. And so we do have a Terraform solution for this that we're getting ready to publish up on that HPC apps repository. It's in some of our other repos out there as well. But we deploy a Lustre file system on GCP, where we combine the metadata server and the management server into one node. And we stick a 1 terabyte PDSSD disk on that metadata server. And then the object storage servers is really the workhorses of the system that are handling all that file I/O. And you can drastically improve the performance of your file I/O if there's enough parallelism there in those file I/O activities by increasing the number of object storage servers or beefing up those systems. Now in our case, we use the N2 standard 16 nodes for the Lustre OSS. And that was really the minimum system size requirement to get all the possible network bandwidth out of those nodes. And I know it says the way we use PDSSDs here, this was just a generic architecture diagram we have. In our particular case for WRF, we're using local SSDs, which are incredibly fast, low latency disks that attach directly to those instances within the Google data centers. So we racked up each of those instances with about 3.5 terabytes of local SSD to get as much performance out of that as we could. So on the next slide here, I'm going to show you some of the differences in the file I/O time in WRF that you can get from one parallelizing the output by changing the I/O form in the WRF nameless file, and then of course adding on top of that, swapping out from using an NFS, a single point mounted NFS file system that we're doing on the controller, to Lustre. So down here is the serial I/O over NFS run. Of course, compared to itself, it's parity. But if I parallelize the I/O by changing the I/O form in WRF, if I'm running at 960 ranks for the CONUS 2.5 benchmark, which is what we're showing here, I get about a factor of 192 better performance here. So the amount of time spent in file I/O drops by a factor of 192. Now, if I'm running at 960 ranks, asynchronous file I/O is embarrassingly parallel, and I'm only getting 192x out of this. I've got some more work to do to get performance out of this. So of course, if you're doing single point NFS, one option on GCP is to increase that disk size as much as you can, but eventually you'll reach a cap in how much that disk can support and how much network bandwidth that the single point NFS connection can handle. And Lustre helps you kind of scale past that, where you can kind of aggregate the bandwidth of multiple VMs on those object storage servers. And in this case, you see we're able to, relative to the initial serial I/O over NFS, get a factor of about 13,000 better than that first setups there. So all this is being said is definitely your file system matters big time. And of course, the nature of how your code is doing the file I/O makes a big difference. Because if I just had serial I/O and I put a Lustre file system in there, this would mean nothing. It just wouldn't help. So thankfully, WRF is one of those applications where you can do parallel file I/O, and you can make this happen. Now, keep in mind with WRF specifically, I know a lot of you do some post-processing stuff here to make different weather products. So of course, do some research. there's some steps that would need to be taken after running WRF. There's a toolkit called Joiner that you can use to stitch those files back together to create the files you need to do analysis and other types of work. We do think that there might be sufficient speed up though in this process to make that actually worth it. All right, so let's take a look at cost and speed comparison here. So on this chart here, we're looking again at CONUS 2.5. And now what we're looking at is how this stuff scales as we increase the number of MPI ranks. So from left to right here, we go from 360 MPI ranks up to 1920. In blue, we're looking at binding the MPI ranks to physical cores, so disable hyperthreading. And in the green, we're looking at binding those ranks to virtual CPUs. So we're actually trying to leverage those hyperthreads, okay? So all in all, if we look at the cost here, which is on the left side, the simulation speed on the right side, no matter what, of course, on the per task basis, binding to the cores, so disabling hyperthreading, gives you better performance on a per task basis, right? And I'll explain what I mean by that in just a second here. And of course, because we're doubling the number of nodes we need to have to run on physical cores, your cost is always going to be a bit higher, and that seems to be a trend that's going to continue if we were to keep growing these problem sizes. We do have a few runs where we've ran at like close to 4,000 ranks. We're working on some that are even a bit larger, but anyways, this is what we've looked at the moment, and generally we expect this trend to continue as you go to larger node sizes. So again, although you can get for both of these configurations, you can get the solution back faster on a per rank basis if you bind to cores. However, if I were to look at these costs here, if I were to, this is a green bar, right? If I'm binding to virtual CPUs, binding to virtual CPUs on 960 instances uses the same number of virtual machines on Google Cloud as running on 480 ranks with those cores. And this goes back to what I was showing in that table a couple slides ago, is that if I have the extra nodes and my problem is big enough so I can expose the parallelism, it's definitely more cost effective just to go ahead and use those vCPUs and use those hyperthreads there. And you'll get the answer back not only faster, because if you compare the green 960 over here for the simulation speed and the blue for 480, again, they're using the same amount of resources, I can get the solution back faster and cheaper if I have enough parallelism to expose. So let's compare this against Cheyenne, which may or may not be a fair comparison, but we're going to do it anyways. So we have, and I'm sorry about the colors here, we did switch up. So the blue here is the binding to the vCPUs on GCP, so using those hyperthreads. Green is binding to the cores, so disabling hyperthreads. And keep in mind here, I know the actual measurement points here for the number of tasks don't line up, but like for example, if I hit 3840, that's going to be somewhere between this 2880 and 5760. And on Cheyenne, we should be somewhere between a factor of 50 faster than reality and 100. But on GCP, we don't break over 25 quite yet. So for me right now, this just, I guess I'll clarify too, on Cheyenne, we are running with GCC 9 as well, and the closest version of OpenMP i4 that we could find, I believe they're on OpenMP 4.05 there. So very similar build stacks, same exact build mechanism there, where there's nothing really that's different in terms of the build. And what all this really suggests to us is there's definitely some work that needs to be done on either the guest operating system that we're configuring to run on Google Cloud, or of course on the Google Cloud engineering side. So we're actively looking into that at the moment. So let's take a look at scaling efficiency here. So remember, scaling efficiency is the idea is like if I double the number of MPI ranks, or I double the amount of resources I'm throwing at a problem, I should get a factor of 2 faster increase in performance. And everything less than that difference is what I'm calculating as a scaling efficiency. So 100% scaling efficiency would mean that basically all the MPI overhead is being hidden somehow, and I'm doing great. Now on Cheyenne, basically by the time we get to 5760 ranks, we're at about 80% scaling efficiency. On GCP, by the time we get to about 3840, we're just hovering above that 30% mark. So again, there's still some networking issues that need to be worked out here. And I've gotten questions about, like, well, how can compact placement policies help us here. So if you're not familiar, what a compact placement policy is on GCP, it's a way to tell Google, I want to have nodes that are as close as together as possible on the server racks at the data center. This allows you to basically put in, when you schedule those resources, to really try to minimize some of the network latency that could be going on in the background. Now, compact placement policies only apply up to 22 instances, and if you're working with 60 virtual CPUs, this only applies to really the bottom half of some of our runs, and it wouldn't address some of these issues down at the larger rank counts. So again, there's still some work that needs to be done. Really, I'm here just to tell you where things are at today and show you how you can reproduce it. Now, there's one other feature we did look at. It was recently announced. It's called Google Virtual NIC. I won't go into too many details here, but this was just something we tried since it was something related to the networking infrastructure, where you can enable this guest operating system feature to try to enable a bit more bandwidth on the networking side. And of course, in hindsight, thinking about this, it's no kidding that it didn't work. As you go to larger rank sizes, the message sizes that you send tend to get smaller, and so you tend to worry less about the actual available bandwidth on a single VM, more so than you care about things like latency for smaller messages that you're sending. But anyway, we tried it, and when I say we tried it, we went through a process to modify our image baking process to tag the image with this gVNIC label, so that it could be enabled on the guest OS, and we did some modifications to the Slurm GCP deployment so that when those nodes come online, when you submit a job, that network interface card type is set to the gVNIC. So what I'm showing here is a time series that depicts two different runs. So what we did is we used Google Cloud Monitoring to measure the aggregated bandwidth between all of the compute nodes while WRF was running. And you can see here, without gVNIC, we're running at about 22 gigabits per second. And of course, because that peak is much narrower, right, that's indicative of the run actually being shorter, so there's less wall time. And then with gVNIC, we lose a little bit of performance there. We're about 14 gigabits per second. So this really wasn't a fruitful avenue, but it did open up some interesting questions for us so we could try to understand what's going on with WRF at this scale. I guess I should mention here, this run was done at 3840 ranks, so it's a fairly large run, fairly expensive to do. But I mean, at this point, what we had wanted to do is really kind of get a survey of how things work out of the box, and of course doing some of the modifications we did to the operating system to really tune things as best we possibly could see on the guest operating system side, and then try to provide some feedback to Google on what could be done better here. Now, of course, I've also gotten feedback, as I mentioned, about the compact placement policies. And while we will be looking into this for some of the smaller runs, of course, the larger runs, the compact placement policies don't apply because you can't get a compact placement policy for more than 22 instances. When we started this project, we were really interested in creating something that others can easily just pick up and run with. And so we weren't necessarily interested in using the Intel compilers, simply because it ends up, in terms of a user workflow, if you don't already have an Intel license, this causes some hurdles for you to get through. And of course, if you want to run at the scale we're at, getting a license for the Intel compilers at that scale is quite expensive. However, since the One API has come out, in the last couple months, we've seen some neat stuff happening on the SPAC repos. The Intel compilers are now available. So we actually have a branch that I'll be pushing up this afternoon, actually, where we're working on trying to do builds with the Intel compilers. We've seen a lot of reports where folks are showing about a 10% improvement in the performance and WRF overall. Not necessarily thinking that this is going to improve the scaling, but it should boost up that initial performance anyways. Now again, we've gotten over the last couple of years, we've gotten a lot of questions about containerization. I'm particularly interested in understanding the impacts of the performance here with containerization, because right now we have on the cloud, you've got the cloud provider's host operating system standing between you and the hardware. Then you've got the guest operating system, which is where we are at today. And when you add containerization, you put just one more thin layer on top of that. And the question always is, well, how much can this affect my scaling? Does it affect the scaling? Does it affect the overall performance of the code? So we're actively looking at adding Docker files to that HPC apps repository and looking at some of those impacts. But of course, doing all this work is just not possible if we don't have some type of collaboration or partnership with the community, which is why I'm here today talking to you guys. I'm really mostly interested in what you want to see. And I want to figure out ways for us at Fluid Numerics to be able to get involved with you guys to make some of this stuff come to fruition. So at this point, I really just want to open the floor up to you guys for any questions you had on any of these slides. Certainly, if you have anything you want to share with me about what you would want to see going on with this project, what other applications you might be interested in, you can always reach out to me. I am Joe at fluidnumerics.com. But I'll go ahead and hang tight here while your questions roll in. Hey Nick, so I'm going to go ahead and just read the question out. So Nick asks, were the price estimates early on based on preemptible or spot instances, or were those on demand? So I'll back up just to fill everyone in. So preemptibles are what they're called on GCP. Spot instances are what they're typically called on Amazon, but they're instances that when you create them, they can be taken away from you at any time. And in this case, no, we were looking at the standard pricing for GCP instances. So this is before any other discounts as well. So, you know, especially if you get into like things like committed use discounts, and you can see if you're in a committed use discount, you're running WRF quite often or other applications quite often, you can see, you know, basically 25% of the costs I showed today is what you can expect. There's sustained use discounts, which are a little bit less generous, but they're pretty good if you rack up enough CPU hours every month. But why we might not go towards preemptibles for tightly coupled applications is you might run a job with 120 nodes with MPI, and one of those nodes might get preempted, and the whole thing has to stop. So MPI is not set up to be able to handle preemptions out of the box. And if you were to try to, there are ways you can work around preemption if you are clever about how you write your batch scripts and how you can set WRF up to restart, where you can take advantage of that. But yeah, if you were to go preemptibles, that definitely would save your costs. And then I guess you'd have to hedge your bets on what your preemption ratio might be in comparison to like what you would pay if you just ran standard. In most cases though, especially for the smaller jobs, if you're at like the 480 ranks, 960 ranks, those moderately sized jobs, you'll likely end up on top. All right, well, if there's no other questions, you guys, again, feel free to reach out to me. I am joe@fluidnumerics.com. Of course, you can follow us on YouTube to keep an eye on what we've got going on. We will be providing some updates in the future, hopefully, on WRF and some other applications we've got going. But again, you can find us on GitHub. You can reach out to me over email. We'd love to chat with you about what your interest is in the cloud and, of course, running geophysical fluid dynamics applications. Thanks again for joining, guys. Really appreciate it. Catch you next time.